Okay, so in this topic, we are going to look at the differentiation of logarithmic functions. In order to understand how to differentiate logarithmic function, we need to understand first of all the laws of logarithms. The first law is, I say, log of a times t. This equals to log of a plus log of t. So whenever you have a multiplication here, this is equivalent to the sum of the individual logarithms. If I tell you log of x over y, it's a division, then I'm going to subtract log x minus log y. And if I tell you log of a power n, this is equivalent to n log a. So, sorry. If I tell you ln of x, you have two functions, ln of fx times gx. This becomes ln of fx plus ln of gx. It's important to note here that ln is log to base e. So if I say ln 5, it means log 5 to base e. How do you calculate this on a calculator? You just have to press to do a change of base, because on the calculator I will have log to base 10, so it's going to be log 5 divided by log e. So the same thing, ln fx divided by gx, this becomes ln of fx minus ln of gx. And if I have ln of fx power n, this becomes n ln of fx. Now, after having looked at the laws of logarithm, how do we carry out the differentiation of logarithm? So the differentiation is, if I say differentiate with respect to x of a function ln, first of all, I will have to differentiate the fx, f dash x. You differentiate the function f with respect to x, and you divide it by fx. Example, if g equals ln of 5x squared plus 2x minus 1, find g dash. So dg by dx, which is also called g dash. I'm going to differentiate this first. Sorry, I'm going to differentiate this first. So this is going to be 10x plus 2 over the function itself. So like we have seen implicit differentiation before, if I have to differentiate with respect to x ln y, so this is going to be equal to this differentiation first of all with respect to y, which is 1 over y, and when I multiply it by dy by x. Examples. Use logarithmic differentiation to differentiate r equal 2x plus 5, 3x minus 2 over x minus 3. So as you can see, we can use a product rule as well, followed by quotient rule. But here I want to use logarithm. So what we have to do now, we have to first of all use another color. Take ln on both sides. So ln r becomes ln of all these terms which will become ln 2x plus 5 plus, I'm going to bring the 2 in form, ln 3x minus 2, and then minus ln x minus 3. Because this one is in the denominator, so I'm going to minus. Now, differentiate with respect to x. So for this one, I'm going to have it as r, the differentiation of r with respect to x. I'm going to have this 1 over r times dr by dx. And then on this side, when I differentiate with respect to x, this becomes 2 over 2x plus 5 plus, I leave the 2 outside. This one becomes 3 over 3x minus 2. And this one becomes x become 1 over x minus. Then dr by dx becomes, you take this r, you multiply it by, you bring it on the other side, r times 2 over 2x plus 5 plus 2 times 3 is 6 over 3x minus 2 minus 1 over x minus. Now you can also bring this r, replace r as above. That is, this is the r here. You can take this, you bring it, and further simplify. But this is the answer. If you want to further simplify, you just replace r as above. So this is a principle of logarithmic differentiation. That is, here you are taking ln on both sides. Where you can use also, like I said, you can use product rule. Another one. If r equal 4e power 3 theta times sec 4 theta over square root 3 theta minus 2. Then find dr by d theta. So again, here we are going to use logarithmic differentiation. What we do, we take ln on both sides. What do you get? Ln r becomes all these now. So I'm going to write ln 4e power 3 beta and then plus, we can multiply here, ln sec of 4 beta, and then minus, I'm going to take the half outside because it says square root, so minus ln 3 theta minus 2. So what happens here? I can further simplify. So ln r equals, now look at this. I can have ln 4, it's a multiplication, plus ln e power 3 theta plus ln sec 4 theta, which remains the same, minus half ln 3 theta minus 2. Now, differentiate with respect to theta. This one will always become 1 over r dr by d theta equals this one now, ln 4 is a constant, this becomes 0. What I will do with this here, ln e power 3 theta, I will bring this 3 theta here. Then ln e. You should know that ln e equals 1. So therefore I'm going to have 3 theta. When I differentiate the 3 theta with respect to 3 theta, with respect to theta, I'm going to get 3. Then plus ln sec 4 theta. Now I need to differentiate this, and when I divide it by sec 4 theta, it's going to be equal to 4 sec 4 theta times 4 theta over sec 4. And then for this part, this minus half becomes here. I leave it. And this becomes, I'm going to have 3 as well here. Hence, dr by d theta. I'm going to multiply the r here. I bring it on this side. Then I'm going to write it as So again, we can replace R as given above and get dr over dv. Now, another example, if ever you are going to have to differentiate so how to differentiate y equals x power x with respect to x? So again, we use this principle of taking ln on both sides. So you are going to have ln y become ln x power x. And this is nothing but ln x ln x. Now you see we have a product here. So what we can do, we can use product rule to work this out. And on our left hand side here, it's going to be equal to 1 over y dy by dx. If you use product rule v du by dx plus u dv by dx, you are going to get 1 plus ln x. So here, dy by dx becomes y times 1 plus x. Since y is x power x, what y write it as? This is the answer. So another example, find dy by dx when x equals -2, given y becomes 2x plus 5 raised to x. So again, what do? We take ln on both sides, ln y becomes ln x ln 2x plus 5. So again, we have u here, v here. For this part, it's going to be always like this. Differentiation of y is 1 over y itself multiplied by dy by dx, chain rule, uv. So this is u. dv by dx, this becomes 2 over 2x plus 5 plus v. du by dx, it remains the same. So I am going to have dy by dx 2x over 2x plus 5 plus ln 2x plus 5. Therefore, dy by dx becomes y, which is 2x plus 5 power x into 2x. This gives me the final answer. Okay, so this is the differentiation of logarithmic function. Whenever you are given an algebraic function, you can take ln on both sides. And when you use the chain rule, the product rule, even sometimes the quotient rule to carry out the differentiation. Okay, now partial differentiation. So we are interested in partially. Here we partially differentiate variables if some of them changes. Example, the volume of a cylinder, like you know, equals pi r square h. So volume changes if either the radius or height will change. Hence, we say that volume V is a function of R and H. We use notation curly, it is like this, to find partial derivative. So here, if P equals pi r square h, then I say partial V, partial R will be equal to 2 pi r h. Or partial V, partial h becomes pi r square. That is, here we are going to treat them as constant. These are called first order partial derivatives. Examples: if t equals 6x cubed plus 5x4 s squared minus 4y squared. 6. Find partial t partial s, partial t partial x, partial t partial y. So partial t partial s, we are going to look at variable s and we treat all the others as constant. This one becomes a constant because we don't have it here. It is not relative to a variable s. So this is a constant, it goes 0. Now I'm going to look at s squared because I'm differentiating with respect to s. So I'm going to bring 2 here. It's going to be equal to 10 x. All these are constant. And this becomes s. Similarly, partial t, partial x. Now the focus is on the variable x. So 4y squared, 6 goes to 0. We don't have them. X cubed. I bring 6 here, 3 here. 18 x squared plus this 4 here. I bring it here. 20 x cubed s squared. Y, with respect to this, all these go to 0. Therefore, it's going to be equal to 8y. So this is how we can actually differentiate partially. If z equals sine of xy, prove that 1 over y partial z partial x equal 1 over x partial z partial y. So what we will have to do, we will have to first find partial z partial x. So you look at this with respect to x, it means y is a constant, so y goes outside. Similarly, partial z partial y becomes x cos of xy. So here, 1 over y partial z partial x become 1 over y. What is partial z partial x? This one. And what is 1 over x partial z partial y? Partial z partial y, it's this one. And this one also is cos of xy. So these two are equal, hence we have proved the relationship. Now let's look at this example. For higher order derivatives, show that when z equals e power minus sine of theta, partial 2z over partial p2 equal minus partial 2z over partial theta 2. And when for b, we have to show this. This is equivalent to so for part A, we have to find partial z partial t. First of all, this makes sine theta constant, therefore this is going to be equal to this. Now, second derivative, I am going to further partially differentiate this with respect to t. So I look at this, I differentiate it once again. So this becomes simply z. Because this is what I'm getting in the beginning, the second partial derivative. Similarly, what is partial z partial theta? Partial z partial theta. Now I'm going to treat e power minus t as constant. So I'm going to have e power minus t cos of theta. And second derivative of this e power minus t sine theta, which is again You see, again equal to z. Therefore, I have worked out the first part. I have a minus here because of cos. Then for the part B, second partial derivative of z with respect to t and theta. So then I'm going to write it like this. Partial z, partial theta, I've already obtained it like this. So I'm going to now partially differentiate with respect to t. This is going to give me minus e power minus t cos theta. Now for the second one, so work out the second, you're going to get the same. So these two are equivalent, and therefore we have already proved for part A and part B.